What do you think? All right, guys, you need to have telescopes. They have telescopes back now. The answer to that question is, of course they did. And if I were to ask you who invented the telescope, some of you guys may say it's Galileo. It's not. All right, Galileo started using the telescopes. He's the first person to actually turn the telescopes to the sky and started to study the Mercury, the sun, and so forth. All right. Telescope was initially invented somewhere in Holland by two glassmakers, whose names I don't remember. By the time Newton was around, which is about a generation later, of course they had telescopes. In fact, Newton built himself a mirror telescope instead of the refracting telescopes that they had back then. So he's talking to his buddies, the astronomers. He say, can you guys just do me a favor if you're not too busy, because life is boring? Just measure the acceleration of gravity for me, right? And his friends were kind of amused, let's say, because Newton is 21, 22 years old. He's real naive. And in a sense that he thought mistakenly that this was something that could be measured, right? Today, it's not a big deal. I mean, if you could get a telescope from Kmart, if you no longer have Kmart, let's say Walmart, cheapest telescope that you could buy, only thing you have to do is literally point and shoot. And it comes with software, all the numbers you need will just appear magically. 350 years ago, they did not have that magic. All right, so he's talking to his buddies, and they say, Newton, buddy, we don't even have Walmart yet. Okay, so you can't do those kind of computations. You can't do those kind of measurements. It's out of the question. But what they were able to measure was just as interesting and fascinating. They were able to measure a deviation from a straight line. So if in the absence of gravity, the moon would go in a straight line. Now, instead of going in a straight line, here's what the moon does. It actually remains on this trajectory, so it deviates from a straight line towards the Earth. So there's a deviation in this direction towards the Earth, a distance of 1/20th of an inch per second. All right, so that's what they were able to measure. This is real impressive. So they were able to measure a 1/20th of an deviation from a straight line towards the Earth from a straight line. Now it's a dilemma. This is what Newton wants them to be able to measure, and this is what they're able to measure. So how do you come up with a mathematical expression that's going to house the acceleration due to gravity with the vertical distance towards the Earth within a certain time period? So he needed a mathematical expression which is going to have g in it, t in it, and the distance y in it. All right, algebra, no good. Trig didn't work. Geometry was useless. So in complete secrecy, he develops a much more mathematical technique, which is otherwise known as calculus today. Out of calculus, he comes up with this equation. It's a free fall equation, guys. All right, and g is the predicted value. It goes in here. Time is your 1 second. It's going to go in here. So the question is, if we were to plug those equations in, this just didn't work. I got overambitious there. Okay, this is good enough. I like the star shape. All right, so if you were to get those equations in, would you get these observed values? So these are the observational. Here's your prediction. Here's your observation. All right, so which means that we need to come up with one more prediction numerically. So it's going to be 1/2. G is this value. It's going to be 0.00273. And RT is going to be 1 second. It's going to be 1 second squared. All right, 1 squared is going to be 1. This number divided by 2 is going to be roughly about 0.001 meter, which is the same as 1 millimeter. And this 1 millimeter is the same as 1/20th of an inch. All right, so what that means is this 1/20th of an inch is the same as this 1/20th of an inch. So this is your prediction. This is your prediction. This is your observation. All right, so that 1/20th of an inch deviation from a straight line, observed straight line, agrees with the predicted value, which means that gravity extends all the way out to the moon. That's it. All right, no arguments. If the numbers match at that point, even if you disagree at that point, you just shut up. You go, okay, this formula is correct. So gravity extends all the way out to the moon. The proof that the gravity extends all the way out to the moon is that 1/20th of an inch deviation from a straight line. This guy at the age of 22, because of his obsession about the apple and the gravity, apple and the moon, he comes up with the laws of motion, comes up with law of gravity, he structures physics into the science that we know today. And then in order to solve this problem, he also invents calculus. You're looking at the picture of the most influential human being who ever lived in the entirety of the human history, guys. You could take the human history literally and divide it into two halves, before Newton and after Newton. Nothing much interesting happened before Newton. People had short, boring lives. All right, life was the same day after day, year after year, century after century, millennium after millennium. After Newton, the science is born. The way he did his physics is exactly the same way we do all sciences today. Applied science becomes technology. As a result, I'm able to make this presentation through Zoom. And look at what we have look what happened within the past 350 years. Only difference between life before Newton and after Newton is all the toys that we got. Life got a lot more interesting thanks to this guy.
Most of us have only experienced a tiny slice of time and space.
Now we got a question. We know gravity extends all the way out to the moon. This guy's not inside an elevator.
Have only experienced a tiny slice.
He's in space. It appears to be weightless. He cannot be weightless in space, can he? And I know what you guys are thinking. Oh, you're thinking, oh, so gravity diminishes, the force of gravity diminishes with distance with respect to the center of the Earth. This guy's in space. Of course, he doesn't weigh as much. Guys, just think of it this way. Which one falls faster? Is it a penny or is it a 400-pound stone in the absence of gravity? Everything is falling at the same rate, right? Which one falls faster? Is it an atom or is it a 400-pound stone? They're still falling at the same rate. Which one falls faster? Is it an electron or is it a 400-pound stone? Regardless, all right? It has nothing to do with weight. All right, so you're in space. You're thinking, oh, the force of gravity diminishes, so it's not going to be zero. So which means that you should still be falling in space. Does gravity really go to zero once you're outside of the atmosphere? Let's take a look. All right, so the astronauts usually orbit Earth 180 miles from the surface of the Earth. All right, so we got the mass of the Earth, the radius of the Earth, plus the distance to the space shuttle. So this d that you're looking at is the distance from the surface of the Earth to the space shuttle. So the question is, what is g? That distance. All right, so the formula gets modified. So what is g? It's get modified. So g is going to depend on the mass of the Earth. It's going to depend on the radial distance all the way to the space shuttle. So it's going to be RE, that's the radius of the Earth, plus the distance to the space shuttle. Now, if it is zero, then you're weightless in space. If it is not, then you cannot be weightless in space. Your bet is, you know, you're not going to be weightless, but you're thinking that your weight is going to be so small, it's going to be negligible. Well, g is not quite zero. It's not quite 10, but it is almost 10. Instead of getting 10, you end up getting almost 9. So what does that mean? So what that means is, if you take a guy here on Earth, some guy who weighs roughly about 216 pounds, and if you were to weigh this guy in space, he's going to weigh about 200 pounds. Guys. In space, this guy's going to lose about 20 pounds. That's it. I got news for you. This guy is not weightless. Far from it. This guy weighs 50 pounds more than I do. All right? This guy weighs 50 pounds more than I do. And he is feeling weightless. He appears weightless. He feels weightless. He acts as if he is weightless. And I don't think it's fair. I want to be able to feel weightless at least once a week, especially back when we used to do in-person education. I mean, I used to work in Shambo, for God's sake. It's 20 minutes from here. And on Monday mornings, the traffic used to suck. That 20-minute trip would take about an hour. I mean, it would have been awesome. Just go out to the balcony, line myself up with this school, and just float to school once a week. I mean, I pay my taxes. That's not too much to ask for. Why is it that these guys are able to float around, and when you actually try to float, you end up falling like a hot bucket of shit? What's going on? I mean, these guys, literally, this guy that you're looking at, this guy still weighs 50 pounds more than I do. These guys are not weightless. Why do they appear weightless if that's the case?
I thought there was a weightless room somehow. I knew that astronauts practiced, and I assumed that there was a place to do it. And I learned that that doesn't exist, but that they can simulate weightlessness in an airplane by doing a parabola, which is sort of like a big roller coaster maneuver in the sky. As you're sort of going over this hump, it sort of tosses you, and then the pilot flies the airplane in an arc that basically flies around you as you are free falling. You really can't wait for the next parabola. I don't know if it's a throwback to...
Okay, guys, what kind of motion is that?
Free fall?
It's free fall. It's projectile motion. Give yourself 5 points on that one. Okay, it's free fall. It's projectile motion. All right, so imagine that you have a ball and you have a second ball right next to each other. This one you drop, and so it's going to land at some point. The other one, you will just project it horizontally, so it's going to go through a projectile motion. Which one is going to land first? Both at the same time, right? All right, both motions are under the influence of gravity. All right, this is free fall, so is this one. So this is the projectile motion. So imagine that you're inside an elevator, boom, the cable snaps. So what does that feel like? Weightless. You will feel weightless. Are you weightless? No, you're feeling weightless. Imagine that you're inside an airplane going through a projectile motion. What does that feel like? Weightless as well. You're not weightless. You're not weightless. You will feel weightless. You will feel weightless. Because you and your environment, in both cases, are falling under the influence of gravity and gravity only. Everything is falling at the same rate. As a result, you will feel weightless. Free fall, under the influence of gravity. All right, so Apollo 13 is the movie that we're making.
Some embryonic sort of recollection that we have.
Notice that everyone is up here and
What?
weightless. They're weightless? Not a chance. They still weigh plenty.
But it's
All right, if anything, they weigh 2 pounds less than what they were on the ground.
very soothing. And
Right now, everything that you see here, everything that you can do inside a falling elevator.
exhilarating. And
I don't recommend it because here they're gonna let them know when they're gonna stop. Free fall, it's not an elevator; it just happens by surprise.
And a lot of fun, because I never got to do this because I was always involved in every shot. But anytime one of the actors was not in a scene, they didn't go and rest somewhere. They went to the back of the aircraft, and on every parabola, they would play Superman because you felt like you were flying. And there were all kinds of zero-G games going on there with frisbees and footballs and stuff that were a lot of fun. But it's an amazing feeling.
All those scenes are shot in free fall.
And always a little bit of a letdown when
in projectile motion.
you finally land and you're walking across the tarmac, and all the usual rules apply.
Awesome. All right, so the next question is, why did these people? So that's what happened. But they were going through a projectile motion, so they were feeling weightless. Why do astronauts appear weightless? Believe it or not, the best explanation came from Newton himself in the book Principia that he wrote. All right, so this explanation you're about to see is based upon his explanation. All right, so this explanation, imagine that you're at the surface of the moon and you have a rifle that can actually fire bullets at varying speeds. Okay, so faster the bullet goes, the further away it's going to travel, right? But at a given speed, the trajectory of the falling bullet is going to match the curvature of the surface of the moon. This bullet is still falling, but it's falling around the moon, which means that this bullet is in orbit around the moon. What that means is unless she takes a step sideways, she's going to end up taking a bullet to the back of her head. The same thing happens around the Earth. When a space shuttle is located 180 miles from the surface of the Earth, while it's moving at 17,500 miles per hour, the trajectory of its projectile motion is going to match the curvature of the surface of the Earth. So if you're on the inside, standing on a scale, this is free fall. Projectile motion is the same as free fall. You will feel weightless, just like the guy inside a falling elevator. Notice that when the cable snaps, reading is going to be 0. You will feel weightless. Are you weightless? You're not. You will just feel weightless. You will appear weightless. That's it. So you're not weightless. You're just appearing weightless. All right, so let's conclude this portion of the lecture. Apple falls because of gravity. That was Newton's obsession. So his question was, if objects fall because of gravity, why doesn't the moon also fall from the sky? Or does it? What do you guys think? So what's the answer to that question? The answer to that question is moon also falls, right? Moon falls in the form of projectile motion. The trajectory of the falling moon is going to match the curvature of the surface of the Earth. So it falls without ever coming closer to the surface of the Earth. All right, so the moon also falls.